Hello, class. My name is Yufei Tao. I'm your uh, first instructor of this course this semester. Um, it's really, really nice to see all of you online. Um, and Today we are going to talk about the first lecture for the course. Okay. So as you can see, we're going to talk about some fundamentals. This has a lot to do with disks, hard disks in particular. Um, so in this slide, you can see a very typical architecture of the computers we're using today. Okay, so you have this CPU, and also you have some memory. And for a typical machine, I would say you have somewhere between 4 GB to 64 GB of memory, and memory access is quite fast. You can implement very efficient algorithms as long as your data fits in the main memory. I guess you probably have heard of some of those algorithms. At this stage of your undergraduate study at NTU. For example, we might be talking about sorting. We might be talking about shortest path algorithms, etc., etc. Okay. However, there was something bad about main memory. This is also called RAM, right? Random access memory. There was something wrong about this RAM. The disadvantage is that if you cut power to the computer, and then all the data in the main memory will be gone. There's no way to find them. There's no more, it's no longer possible to retrieve what you had in the main memory before the power cut. So you know how to deal with this situation. So that's basically the reason why you need a hard disk in your computer. Okay, so this hard disk here uses a different technology to store the data. So basically, for example, traditional hard disks use magnetic theory to store data, right? Um, so the key difference between hard disks and the main memory is that the data on the hard disk is able to persist even if there's no power. You are not going to lose the data. Okay. So overall, you can see this architecture really makes sense, right? Because uh, the purpose of a hard disk is to increase the storage capacity, and also, um, as I said, to allow data to persist um, even if there's no power. However, access to the hard disk, as you know, is typically much slower than accesses to main memory, and the main memory is closer to the CPU. So if you need to compute stuff, this computation takes place inside the CPU. Okay, and this CPU will read data from the memory, not from the disk, right? So as you can see, there is a hierarchy here. Um, when you turn on your computer, data is here, and then eventually data will have to move to inside the CPU. The terminology there is cache. Okay, there are some registers inside the CPU. So the data will have to move from here all the way up to here, and it will have to go through the main memory. Okay, so this is, I would say, a three-level hierarchy of the computing architecture we're using today. Okay. All right. So why did I start the whole course with that slide? Well, this is because in this course, we are going to talk a lot about disk-based database systems. Okay. Um, As you can see, the explanation here, this means data is stored on disk rather than in main memory. Okay. Well, just so you know, there are database systems that store data in the main memory. And such kind of databases will be able to do things faster because data is in the main memory and therefore can be retrieved faster. It doesn't necessarily mean that such kind of systems are better because these systems, they also have their own limitations or disadvantages. First, the memory capacity really limits how large your data sets can be, right? So as I said, some of your laptops will be able to accommodate 64 gigabytes of memory data. So basically, that's how large your database is allowed to be. But 64 gigabytes is really nothing in today's big data era. Today, you want to store much larger data sets, and for that purposes, this main memory database would not be a good fit. Now, that is only the first limitation. Another very serious limitation of main memory databases is that, as I said, memory data is not persistent. So such kind of systems will have to face the challenge of uh, not losing data in the presence of power outage. Okay. So at first glance, well, as you can imagine, right, this is quite difficult because at first glance, this doesn't appear possible, right? Because really, this power loss could happen anytime, right? How can you, how why would it even be possible to prevent data loss in such a system? Well, there are some clever tricks to achieve that purpose. Okay, but such kind of systems will not be the main focus of this course. Well, it's worth pointing out that disk-based database systems are still the dominant choice for most applications today, in particular banking applications, right? So this is one of the most important applications of database systems because we don't want our bank account balances to get corrupted anyhow. Okay, so today this course its focus is on disk-based systems. Okay, very good. Well, you see, I have been talking a lot about disks. That makes you wonder, is it really different from what you might already know? Because I know many of you have been very well trained in terms of data structures and algorithms, right? You probably know a lot of algorithms that are designed to optimize CPU performance, right? So, for example, if we talk about sorting, and then you might be able to recall time complexities like n log n, that kind of stuff. Um, n log n time is actually the best you can do. So all these things, right? And they make you wonder. I mean, why do we really have to spend time learning anything new, right? It's just disk and CPU. Are there really differences? Well, um, the answer is a big yes. Okay, it's a resounding yes. Okay. Um, Well, one very important purpose of this course is to um, tell you why this is true and also tell you the underlying principles behind designing algorithms that are fast in terms of disk performance. Okay. However, we're not there yet. Okay, so this is the first lecture. This is the fundamental part. And I can tell you we're not there yet. Okay, if I commence talking about uh, disk-based algorithms right away, you're not going to get really, really impressed. You not really get convinced, let's say, that such algorithms are necessary. What stands between you and those algorithms is a deeper understanding about disks. And this is what I'm going to do. In order to fully understand how come we cannot simply migrate our knowledge about CPU oriented algorithms to the disk environment, is that in disks, when we have to deal with disks, we do not really read information in terms of words. Okay, we read information in terms of blocks. Okay, so this is a very high level but very important message for you. And at the end of today's talk, you can come back, you can rewind the video, and you can come back to this slide and check for yourself if you consider this is something true. Okay. Well, it's going to take a while for me to convince you about this, for anyone to convince you about this. For that purpose, we really have to talk about how a disk works. Okay. So I'm going to spend a few slides on this. I'm going to peel off the skin one layer at a time. Okay, if you understand what I'm saying. Okay, and hopefully, after a number of slides, you have a very good understanding about how hard disks work. Okay, so let's get started. Well, if you open up your hard disk, and then you will see that the storage medium takes the form of a concentric circle. Okay, so this is the stuff here. As you can see, this is the inner edge of this medium, and this is the outer edge. Okay, so it's a concentric circle. All right, so if you, well, at my time, my home used to have this black music record, and you play. It's not CD. This is something that came before CD. It's black. It's big. It's round. So I don't know if you have a chance uh, to see such music records. Okay, but if you go online, if you Google for black music records, old time, and then you will see what I mean. Okay, so once again, it's a annulus. Okay, so it's a ring, right? And inside the annulus you have the magnetism medium, and you can and scientists and engineers have been able to figure out ways to store information in here. Okay, so this is the medium. All right, so this is the hard disk. All right, good. Well, let's look into the annulus here. And you can imagine that the annulus has been sort of like divided into more concentric circles. Okay, so here I show you a simple example with just three concentric circles. So these three concentric circles are referred to as tracks. Okay, so we have three tracks here, and this is the red track, blue track, and green track. Okay. Um, and I can tell you data is stored along the tracks. Okay. So some of you would ask, okay, what about the gaps here? Right? Do we have data over there? Well, yes and no. Okay. No, in the sense that really data is stored along the tracks, and data is not stored on the gaps. All right. However, yes, in the sense that in real life, the tracks are much denser. Okay, tracks are much closer to each other. All right, so here, for you to see things clearly, you can see big gaps between two tracks. But um, in practice, the gaps are much smaller. Okay, so don't worry, you are not really wasting a lot of space for storing data. Okay, scientists and engineers have tried very hard to really maximize, how much data can be stored on a disk. Okay, but what is really important is that each of these concentric circles is called a track. Okay, and also data. Once again, data is stored along the tracks. Okay, so that's the first thing we got to understand. Very nice. All right, now this is the second thing. Okay, so if you look at every track is uh, divided into a lot of disjoint arcs. Okay, so as you can see here is an arc, right? So this arc is called a sector. Okay, so you have many sectors along each track. Okay, so I can tell you the hardware, I mean, this hard disk, right? This is a piece of hardware. The hardware is designed in such a way that the disk will be able to read things at the unit of sector, okay? And every sector is a number of bytes. Every sector stores a sequence of bytes, okay? And the number of bytes in each sector is the same, okay? So this is a specification of the disk, okay? So once again, track, this concept, do not get confused. This track is a concentric circle. And this track is divided into lots of disjoint arcs, okay? And every arc is called a sector, right? So you know what bytes are, right? So each byte is a sequence of 8 bits. You know that, right? So every sector here consists of a fixed number of bytes, and therefore a fixed number of bits. So for example, some common values are here. The first common value is 512. Okay, so this is like 512 bytes here. Once again, if you care about bits, and then it's 512 times 8. Okay, so that's how many bits you have in a sector. Okay, another common value is this. Okay, so this is a specification of the hard disk you are using. Okay, so this is the second concept here. Okay, very nice. Now let's proceed. Um, Here uh, talks about how the hard disk will be able to identify the sectors. Well, since as I told you, uh, uh, sectors are the unit of reading and writing for a hard disk. Okay, so the hard disk, this this hardware is designed in such a manner. Okay, and therefore there must be a way for let's say an application to name a particular sector and tell this piece of machine, this piece of hardware, that this is the particular sector I like to read or write, right? So there must be an ID assigned to every sector. Okay. So one convenient way to imagine about the ID is to first specify which track this sector lies in, okay? And then within the track, what is the sequence number of the sector, okay? So here, I'm just showing you an example. Say this is track number 2, the blue track, right? You remember I had 3 tracks, right? So this is the red track, and then the blue track, and then the green track there, right? So every track has a sequence number, obviously, and this is the second one. And inside this track, we have sectors. And as you can see, I'm showing you some sequence numbers of 4 sectors, right? So 312, 313, and so on and so forth, right? So if you wonder where is 1, maybe 1 is here, okay? And it starts from 1, and the largest sequence number is equivalent to how many sectors you have on a track. Okay, good. So if you look at this combination, this pair, um, you should get convinced. It's quite obvious that it's quite obvious that this pair is sufficient for an application to really identify particular sector, right? You can go to any sector and you can name the sector in this manner so that people, I mean, applications can identify it. Okay, so this is the ID. Okay, nice. All right. Now this brings us to a very, very important concept, and this is the block. Okay, the concept of block. If you still remember several slides back, I said IO, I mean, these are disk oriented algorithms. They are different from CPU algorithms because um, disk oriented algorithms read information in blocks, while CPU oriented algorithms read information in words. Okay, so here, this is your um, opportunity to learn about what blocks are. Okay, so here is a formal definition. Okay, a block is a set of sectors. Okay, actually consecutive sectors. Okay, so here in my example, I have four sectors in a block. Okay, so this four is not necessary. It's not necessarily four. Okay, it could be some other number, and I will explain how this number and when this number is decided. Okay, but it's important to remember that all the blocks, they are equally long because they contain exactly the same number of sectors. Okay, so the number of bytes in a block is called the block size. Okay, so the block size is equivalent to the product of two things. The first is, the number of sectors in a block times the number of bytes. Okay, the number of bytes in a sector. So this is, the definition of block size. Okay, all right. So how many bytes you have in a block? Okay. All right, so I told you before that sector, still remember, right? Sector is the unit of access for the hard disk, okay, as a piece of hardware, okay, as a piece of hardware. Now, what is a block? A block is unit of access for the operating system. All right, so these are two different things, okay? So, so let me write it down here. Sectors, so this is the unit of access, uh, that comes with the hard disk, okay, for the hard disk, for the disk. Okay, so block is the unit of access for the operating system, okay, for the operating system. Well, I don't know if you have experience about disk formatting. You buy a hard disk, a new hard disk, and before you can use it, you have to format it. Okay, so one important thing that is done in formatting a hard disk is to determine the block size. And typical block size value is 4K bytes. By the way, 4K is roughly, you know, um, 4096. 1K is 2 to the power of 10, right? So that's 1024. So this is four times that, right? And it could also be something larger, 64, 64 KB. Okay, so that would be 64 times 2 to the power of 10. Okay, so the block size is determined at the time of formatting the hard disk. Okay, so this is something very important. Now, the OS does not really have to align with the hard disk in the sense that, as I said, the hard disk says, well, I would like you to read information one sector at a time. But the operating system does not really have to do that. The operating system can say, okay, I will take a another granularity, and I will combine multiple sectors into a block. In my example, the answer is four sectors in a block. So the operating system has every right to say, so each time I access the disk, I will always take 4 sectors. Or you might say, every time I access the disk, I will always take 8 sectors. It really depends on the operating system. Okay. And a typical value used by Windows, if I'm not mistaken, a typical value is 4 KB. Okay, 4 KB. In other words, every time a Windows system goes to the disk, it will always read multiple sectors because one sector is shorter than 1K, smaller than 4 KB, right? So a block consists of multiple sectors. Okay. All right, so 2 very important concepts, sector and block. Okay, I don't want you to mix them up. Okay, so I don't want you to confuse them. Okay, and why is this happening? Okay, why is this happening? All right, so let's move on. Okay, eventually you will understand why things are designed this way. So before I tell you more, let me first explain that every block also comes with an address. Okay, so just like sectors, you need something to ID every block. Okay, so um, in order to uh, identify a block, so as you already know, uh, blocks are created during formatting, right? So these blocks are disjoint, and every block contains the same number of sectors, right? So we can use the ID of the first sector in the block to serve as the starting address of the block, right? So that will also we don't say starting address, we just say, that's the address of the block, right? So the formal definition is this: every block, its address is just the ID of the first sector of the block, right? So for this block, for example, what is its address? It's 2312. Why 2? Because this is track number 2, and this is the sector sequence number 312, right? So this is indeed the ID of the first sector inside this block. Okay, good. Very nice. Okay, so we are another step closer to explaining how you can retrieve a block of data. Okay, almost. We're almost there. There's still one thing that requires explanation. Okay, so I talked about the concentric circle, right? So now I can tell you this that this concentric circle is known as the platter. Platter. Okay, so basically a round disk. But other than the platter, there's another very important thing that reads or writes data, and this is the head here. Okay, the platter keeps spinning. Okay, so this is this is the pole or the stick that's at the center of the platter, and this platter spins really, really fast. Okay. Um, well, this head contains some kind of magnetic sensor, and it's able to see very quickly what is going under it. Okay, so as data goes under it, this head is going to pick up information and we'll be able to see, oh, that's 0 or 1. So that's reading. Okay. Conversely, this head will also be able to put down information onto the sectors that are going underneath it. Okay, so that's called writing. All right, very nice. Well, you see, at least one thing has to be spinning, right? So the disk, as I said, the disk the platter is spinning very fast. Okay, but you don't really need two things to be spinning, right? It's unnecessary. So one thing is enough to spin only one thing, but not two things, right? So indeed, the head does not spin. Okay, so the head stays here. The head is it doesn't move when it's reading or writing. It simply stays there and waits the sectors to under flow under it. Okay, so this is how things work. But wait, I told you before that there are multiple tracks inside the disk, right? So for example, this is I showed you before 3 tracks, right? In practice, you have much more, but definitely more than 1 track, right? So now the thing is, the head must be somehow movable. Why? Because if the head always stays at this position, and then it will be able to read only 1 track, right? Because once again, it can only read the sectors flowing under it. Okay, and if the head is here, it will not be able to read the blue track. Okay, so in order to read the blue track, the head will have to move. Okay, so this is the reason why there is a moving system for the head. Okay, so this is the moving system here. Let me show you. So here there's an arm. Okay, so this arm can move the head vertically. Okay, vertically. So more specifically, I have this dotted line here, as you can see. Okay, so this dotted line does not spin. All right, so the dotted line stays here forever, and the platter keeps spinning. Remember that. All right. However, what the head is allowed to do, what the head is capable of doing, is to move along, this segment here. It can stop at any position along here. Okay, so this will allow the head to reach the position of any track. Okay, so if you want to read track number 1, the head will move to, let's say, here, and then wait for the sectors of this track to go under, right? And if you want to read track number 2, and then the head will have to move here, and so on and so forth. Okay, so this is a very important feature of the design of our hard disks today. Okay, nice. Finally, I am able to clarify how a disk works, how to read a sector. Now, this slide is about a sector. Still remember what a sector is? Okay, I said it multiple times already, right? So this is the unit of access for the hard disk as a piece of hardware. Okay, so you cannot confuse this with blocks. Okay, so blocks is the unit of access, for the operating system. Okay, so here we're talking about the hard disk. Okay. If you want to read a particular sector, of course, you have to provide the address. Okay, so the address, this is the track number, and this is the sequence number. Now, once you have provided the address, the hardware starts to serve this request. And in order to do so, the hard disk will have to perform 3 steps. Okay, so here, 1, 2, 3. And the step number 1 is to move the head. Okay, to move the head. And then step number 2 is to wait, wait for spinning. And step number 3 is to read and write. You see, in this slide, I did not go into the details. I just want you to remember 3 things. Okay, so the first step is to move the head, and the second is to wait, and the third is to actually perform the reading or writing. Okay, so I will use the next 2 slides to clarify each step. Okay, so starting with the first, okay, move. Now, what do I mean by moving? Well, this is something I told you before already. remember the head can only move along this segment. And currently, the head may not be at the right track, right? So you are asking for track number 2, but currently, the head is on track number 1, and so wrong track. Okay, so you cannot really read the sectors of that track. So what do you have to do? Well, first of all, you have to move the head. So that's exactly what step 1 is trying to do. Okay, so as you can see, if the starting situation is this, and then this is like a moment later. You see what I mean? A short moment. But what has happened in this little period is that the head has moved from here, basically here, to the position of track number 2. Okay, so that's what it does. But remember, the platter keeps spinning, right? It's not going to, you know, stay stationary or stay static, right? It keeps moving. So that's why you see this track, which is, this is sector. This is the sector we're trying to read, right? 312. So before it was here, and then, at the end of this little period, the sector might have come all the way to this position here. Okay, so this should be a very realistic realistic illustration of what's going on, right? So this is the step number 1. So remember, the step number 1 is to move the head, okay, from its current position to the target track, okay? Well, this takes time. Okay, this takes time. This is mechanic movement. Mechanic movements are very slow because they are succumb to uh, physical laws, right? So no matter how smart you are, there is resistance and everything. So it's not possible to really accelerate mechanical movements significantly. So this takes time. Okay, so the machine will have to be moving. Okay, some metal grinding stuff going on inside the hardware, and the amount of time to perform the movement is called seek time. Now, this seek time is also very intuitive, right? Because this is the time of seeking the right track, right? The seek time. Good. So step number 1. All right. So now we are in this situation. Now let's continue from this situation. Okay. Now, the hard disk, in order to service your request, will have to start performing step number 2. Okay, step number 2 is to wait for the sector to come underneath. Okay, you see what I mean? Wait for the sector to come underneath. Look, so after the first step, the head is in position. Okay, track number 2, that's good. However, the platter uh, keeps spinning, and currently the sector is still far away from this head, right? So the hard disk will have to, I mean, the head cannot read anything yet, right? It will have to wait a little bit uh, for the uh, for the sector to come from this position all the way to the position right underneath the head. Okay, so this is the second step, and this second step also takes time. Okay, so the amount of time it takes is the wait time. Okay, because uh, during this moment, the head doesn't move, right? So the sector um, moves, right? So the head simply waits for the sector, and therefore it's called the wait time. Okay. By the way, the wait time is also expensive. Why? Because this is also mechanical. Okay, mechanical. I mean, it's spinning stuff, right? So this is also quite expensive. How expensive? We'll see about that later. Okay. Now, this is step number 3. Sorry, this is step number 2. Now, step number 3 is something that's much faster. Okay, as I said, this head has the capability of sensing what's underneath, what's passing through underneath it, right? So, and by doing that, essentially, it picks up information that's stored inside the sector, information is basically either 0 or 1, right? But a sequence of such kind of bits. But this sequence passes through underneath the head as the disk spins, and therefore, as you can see, um, the head will be able to pick up the entire sector. Okay, so this is step number 3. Okay. Well, I can tell you step number 3 is significantly faster than step number 1 and step number 2 because it involves very, very little mechanical movement. Basically, the only thing that's mechanical here is, uh, the platter will have to spin a little bit, for the entire sector to pass under the head, right? So that's the only thing um, required. However, since the sector is very short, you can expect that this part is, very, very fast. So it's basically negligible. But of course, something will also have to happen for the hard disk to pass the information along um, the wire to the other parts of the machine, for example, memory, right? However, this part is also very fast. Why? Because this is not mechanical. This is electric. Okay, electric. So if it's electric, and then things can get much much faster. And also human beings are very good at improving electric stuff. Okay, so basically the number of transistors, that kind of stuff, right? So people have created a lot of wonderful ideas. So these things are basically getting faster and faster. Okay. However, as I said, mechanical movements, they are very difficult to improve because basically you are fighting against physics. Okay. So I hope this makes it clear. Step 1, 2, 3, and let's take another look at these 3 steps. As you can see, the first step, you have to seek the track, right? So you have to move the head to the position of the track that you want to read. Excuse me. And step number 2, you have to keep the head there, and then you wait for the sector to come to it. Okay. And step number 3, this is something quite fast. You simply read or write the sector. Okay, very nice. Now remember, this is how the machine, how by machine I mean the hard disk, how the hard disk reads a sector. Okay. However, the OS very, very seldom reads just one sector, almost never. Okay. For the OS, the unit of access is a block. Okay. A block consists of an integer number of sectors. Okay. So as I said, a typical value for block size is 4K bytes. Okay. And maybe one sector is like half K bytes. Okay. That's 0.5 K bytes. So in that case, you can imagine that a block will consist of 8 sectors, right? So just to give you an idea. Um, and how is this performed, right? So this is performed in a way that is basically the same as reading a sector. Also, it consists of 3 parts. Okay, so the first part is the seek time, right? Again, you have to seek the track where the block is, right? So this is the seek process, the seek time. And then you have to wait, right? Because the starting sector of this block may be far away from the head, right? So it will have to wait for the head to spin over to under the head. So that is the wait that the waiting process, right? So the duration of this waiting process is the wait time. Okay. And still, step number 3 is simply to pick up the information for reading. If you want to write, basically write the information, right? Uh, but the thing is, here you are not reading just one sector, right? You may be reading multiple sectors. So in my earlier example, you have to read 8 sectors, right? But the thing is only 8 sectors, right? So that could be involving a little bit of more mechanical movement than just one sector. However, 8 is not really that large a number. You see what I mean? So the amount of mechanical movement is still quite limited. So the time of that is still very short. Okay, and also there's some electric stuff happening because the circuit will have to pass the information to the memory, whatever, some other parts of the machine. But that part is electric and therefore takes very little time. Okay. So now, with all this explanation, finally, for the very first time, I'm able to say the amount of time to access a block. By the way, when I say access, I mean either read or write. Okay, so the amount of time to do that consists of three components. Right, the first component is the seek time, and the second component is wait time, and then finally, the block transfer time. So that is basically the time of step number 3. Okay, cool. All right. So that brings us to this equation here. Okay, seek time, wait time, and block transfer time, right? So as I already explained, the first two components are typically quite expensive, okay, because they are mechanical, okay? How expensive? Now I can give you some numbers. Of course, the seek time may not be the same for every IO, right? So for, I'm sorry, I said IO. I haven't really introduced IO yet. I should say for every request, a block access request, right? Because why? Because it really depends on where the head currently is and where the target track is, right? So there is a distance for the head to travel from its current position to the target track position, right? However, we don't really want to get so detailed, and it will be quite sufficient to take some average value. And I can tell you, I mean, if you look at, say, a lot of such kind of requests that are happening in the life of this hard disk, and then I can tell you, by statistics, right? So the average seek time will be somewhere around 5 milliseconds or 5 ms. Okay, 5 milliseconds. Okay. Well, for human beings, 5 ms is a very, very short amount of time, right? So you would say, hey, that's not too bad. Well, CPU is not human being. Okay, 5 milliseconds is like an age for the CPU. The CPU can do a lot of good stuff within 5 ms. Okay, so this is really, really, really a very lengthy amount of time. Okay. Well, likewise, for wait time, again, that depends on individual requests. Um, um, a rule of thumb is to take the average. The average wait time is also somewhere around 5 milliseconds. So if you add these two numbers up, that gives you like 10 milliseconds already. So what is that? What does this mean? This basically means if you think about 1 second, so how many blocks would you be able to read? Well, every block on average would take at least 10 milliseconds, right? So that if you do the math, you know within 1 second you can basically read just 100 blocks. Okay, I don't think that's fast at all. Right. So now you can understand. I believe you can understand much better now why disk accesses are always performed in blocks. Okay, why? Because every time you have to move the head, every time you have to wait for the sector to arrive, that's a huge amount of overhead. And it makes no sense at all to spend that much overhead every single time you access a word. So you would like to do this in a bulk manner, bulk, B-U-L-K, right? Bulk manner, right? So basically the mentality, the mindset is, well, since we're going to pay a huge amount of money every time we go there, we better fetch more than just one word. Okay, so that's basically the idea. Okay, so there are also reasons why the Windows operating system would choose something like 4 KB as the default block size. Okay, because after some calculation, actually the calculation doesn't have to be complicated. Basically, it's a back of an envelope calculation. So you do that, and then you see, well, this block size, uh, maybe 4 KB, turns out to be a suitable value. Okay, so that will be good enough to justify this 10 milliseconds. Okay, so that's large. That's not too large. Okay, that's not too small. I'm sorry, but on the other hand, it's not too large. You cannot really set it to something crazily large, right? If you say, oh, let's set it to 1 MB, and maybe the data transfer time will no longer be negligible. Okay, so after some considerations, now you can understand how the block sizes are chosen. Okay, so once again, just to remind you, the block transfer time is quite small. Okay. Okay, very nice. So after this explanation, um, I hope you have got a pretty good understanding about why disk accesses are small. Okay. So now this slide, I'm going to formally define the notion of I/O. Okay, so before I define the notion, let me introduce this symbol, lambda. I told you, right? Every block has the same number of bytes. This is called the block size. Okay, how do you calculate the block size? This is the sector size. Not how many words in a sector, right? The sector size times the number of sectors in a block. Okay, so that's the lambda here. Okay, so the OS always reads accesses the disk in terms of blocks. Okay, and every access can be either a read access or a write access. Okay, so basically a read access is called a read IO. By the way, this IO stands for input output. Okay, and a write access is defined to be a write IO. Okay, so if you want things to be more specific, you can say that a read IO, well, goes to a particular block, right? Because you have to give a block address, right? You have to tell the disk which block you are reading, right? And then bring the content of the block. So that's, you know, lambda uh, bytes, right? The block size. You have to bring, the entire content within that block into, the memory. Okay, so that's what you do. So write IO is the opposite. Inside the memory, you already have an array of lambda bytes, which you are going to write to a particular block, right? So you have to give the address of this block and say, okay, I'm going to use this sequence of lambda bytes to overwrite the original content of the block. And that's defined as a write IO. Okay. All right. So oftentimes I would use the term IO to refer collectively to, either read IO or a write IO. Okay. All right. Now, this is the last slide of the first lecture. So I put this message in a red box. I wanted to uh, be very obvious to you, to look very obvious to something difficult to miss, right? So I can tell you, database algorithms, they are designed to minimize the I/O time, not the CPU time. In fact, for such kind of algorithms, the CPU time is typically negligible. Okay, it's not even worth talking about it. To give you an idea what I mean by negligible, it's like, say, the database algorithm, I mean, this IO time, maybe it's 1 hour, okay, 1 hour. And how long is the CPU time? Well, maybe just a few seconds. Okay, so that's maybe less than a few seconds. So that's, 1 hour is the 3,600 seconds, right? So that's pretty much the difference. It's like less than 1%. Okay, so CPU time is very rarely the concern. Okay. All right, so finish today's lecture. Let me just point out once again that main memory algorithms are designed to minimize CPU time, and they can be very slow when the data is not in the memory, it's in the disk. Okay, so for example, let's say I have n numbers on disk, okay, not in the memory. N can be extremely large. Okay, so if you apply quicksort, which is a wonderful sorting algorithm in the main memory, right? If you want to perform quicksort, we know in main memory it performs n log n operations, right? Because it finishes in n log n time, so that's pretty nice. However, in the hard disk, this would imply that it would need to perform n log n IOs. And this is horrible because you can do the math, right? I told you every IO would take about 10 milliseconds to finish. So every second you can basically perform like 100 IO. So if n is large, then you can basically do the math and tell you, you know, how many seconds you will need to finish this algorithm. Okay, so that's the difference in the principles. Um, okay, of algorithm design, okay, between disk and memory. So later in this course, we're going to learn another algorithm to perform sorting on disk much faster. How much times faster? So basically lambda times. Now remember, lambda is the block size, how many words you have in the block. Typically that's at the order of thousands, right? So in other words, if you apply the principles appropriately, you can expect to improve the quicksort algorithm by 1,000 times. Okay, so that's the difference. All right, so thank you very much for listening. So that's the end of the first lecture.